Now we come to Lusin's theorem. As I mentioned before, this is Littlewood's second principle, the precise version of Littlewood's second principle, and the statement is that if f is an L1 complex valued L1 function on Rd, then given any epsilon greater than 0, there exists a Lebesgue measurable set E such that the measure of E is less than or equal to epsilon, and the restriction of f to E complement is continuous on E complement. So this is what is meant by saying that any L1 function is almost continuous. So this is Littlewood's second principle, which says that any L1 function is almost continuous, and by almost we mean this precise statement that given any epsilon you can find a set E of measure less than or equal to epsilon such that the restriction of f on the complement of that set is continuous on that set. So one cautionary remark. So this statement of Lusin's theorem does not imply that f is continuous on points in E complement when viewed as a function from the whole of Rd to C. So it's not that f is continuous at points of E complement when it is viewed as a function from the whole of Rd to C, but rather it is only the restriction of f to E complement which is continuous on the restricted set E complement. So what is the difference? So for example, the indicator function of the rational numbers in R is discontinuous at all points, in R, and it is an L1 function because the measure of the rationals is 0. So chi q is an L1 function. On the other hand, for any set of finite measure E, chi q is not continuous on R minus E because it's not continuous anywhere in R when it is viewed as a function from R. However, the restriction of this indicator function when restricted to the complement of the rationals, this is identically 0 and therefore continuous when viewed from the complement of the rational sets. So thus continuous when viewed as a map from, so this restricted map is from the complement of Q to C. So this shows that you can have this statement of Lusin's theorem does not imply that f is continuous on points in E complement when viewed from the entire domain Rd with values in complex number. To prove Lusin's theorem, we need a preparatory lemma about approximation of L1 functions. So this is our lemma, and it's interesting in its own right, but here we will use it to prove Lusin's theorem. So it has three parts. So first we take an L1 function f and fix an epsilon greater than 0, Then the first part says that there exists a simple measurable function s such that the L1 norm of f minus s is less than or equal to epsilon. Then the second part is that there exists a step function c such that norm of f minus c L1 norm is less than or equal to epsilon. Here a step function is a finite linear combination of indicator functions of boxes bi. So the difference between a simple measurable function and a step function is that simple measurable functions are defined with finite linear combinations of indicator functions of any measurable sets of finite or infinite measure, but here for a step function we only allow finite linear combination of indicator functions of boxes. So it's very close to what we called piecewise constant functions, but here there is no partition of a single box, and this is a more general concept than piecewise constant functions. So these are called step functions. And the third part is that there is a continuous function with compact support such that the norm of f minus g is less than or equal to epsilon. So remember that the compact support condition means that support of g, which is defined as the set of points such that gx is not equal to 0, and you take the closure of this set. So this is called the support of this function g, and this is compact. So when this is compact, we say that g is of compact support, or g is a compactly supported function. So in the third part we have that there is a continuous function with compact support g such that the L1 norm is less than or equal to epsilon. So all these three are approximations of L1 functions in the L1 norm with different kinds of different classes of functions. So let's look at the proofs for these statements. So for the first part, we note that if f is unsigned, so in the case of unsigned measurable function, measurable L1 function, then the existence of s, the existence of a simple function s such that the L1 norm less than or equal to epsilon is follows from the definition, follows from the definition of the Lebesgue unsigned Lebesgue integral, because the unsigned Lebesgue integral was defined as the supremum of all simple functions which are bounded above pointwise by f, and you take the simple Lebesgue integral of those simple functions, and you get, when you take the supremum, you get the Lebesgue integral of f. So this is almost by definition of the Lebesgue integral for unsigned measurable functions. Now if f is real valued, then we can write f as f plus minus f minus in the positive and negative parts, and then choose, because these are now unsigned measurable functions, both of these are unsigned measurable functions, and then we can use the part we have already shown for unsigned measurable functions. So now choose s plus and s minus simple functions. So whenever I say simple functions, I am meaning simple measurable simple functions such that norm of f plus minus f s plus L1 norm is less than or equal to, say, epsilon by 2, and similarly for s minus and f minus, the L1 norm is less than or equal to epsilon by 2. And then if we set s as s plus minus s minus, then this is a simple function, and we have f minus s, the L1 norm, is equal to f plus minus s plus minus f minus minus s minus. So if we take the L1 norm by triangle inequality, we will have that this is less than or equal to f plus minus s plus plus f minus minus s minus L1 norms, and these are less than or equal to epsilon by 2 each. So this is less than or equal to epsilon. So once we have shown this for unsigned measurable functions, the real valued case follows almost immediately, and similarly we can extend this. We can extend this to complex measurable functions, measurable L1 functions. So notice that here we need, even for the existence of the simple function for the unsigned case, for the unsigned measurable case, we need an L1 function, because we need the Lebesgue integral to be finite in order to write this inequality of f minus s, the L1 norm of f minus s less than or equal to epsilon. So here we have used that f is an L1 function. So we have shown that we can extend this to complex valued L1 functions as well, just by separately treating the real part and imaginary part of the complex measurable function, by treating the real and imaginary parts of the complex measurable function f. So this proves the first part. For the second part, we have to find a step function. So we have to show that given epsilon, there exists a step function c from Rd to C, such that norm of f minus c, L1 norm, is less than or equal to epsilon. So again we can reduce to the case of unsigned measurable functions. Case of unsigned measurable function, and because of the first part, due to 1, it suffices to show the inequality. So let me write it as 1. So the inequality 1, for f simple. If you have a simple function and if you show that there exists a step function which is close to a simple function, then we can deduce it for any unsigned measurable function because of the first part, because then we can choose S simple and C step function such that the norm of f minus s is less than or equal to epsilon by 2 and norm of f s minus c is less than or equal to epsilon by 2, which implies that the norm of f minus c is less than or equal to epsilon by the triangle inequality. So, this triangle inequality, when I say triangle inequality, I do not mean, so let me write it here as a remark. By triangle inequality here, we mean that if f and g are L1 functions, then the norm of f plus g or f minus g L1 is less than or equal to norm of L1 norm of f plus L1 norm of g. So, this is what we have used here to deduce that f minus c L1 norm is less than or equal to epsilon. So, it suffices to show the case when we have reduced it to the case when f is simple, and now we further reduce it to the case when the simple function s is a single indicator function of a measurable set of finite measure. So, suppose that f is chi e with the measure being finite, so that f is in L1. So, this is a special case of a simple function which is just an indicator function of a set with measure with a finite measure. So, here again we are going to use Littlewood's first principle, which is that every measurable set of finite measure is almost a finite union of boxes, or almost elementary. This is elementary. So, how do we show this? So, let us give a short proof. So, if measure of E is finite, this implies that there exists a collection of boxes bi, I equal to 1 to infinity, countably many boxes, such that the sum, so first that E is covered by these boxes, the union of these boxes, and then the sum I equal to 1 to infinity of the measures of these boxes bi is less than or equal to the measure of E plus epsilon. So, this is from the definition of the Lebesgue outer measure. Definition of the Lebesgue outer measure, and this also implies that this sum is finite, which means that by the Cauchy criterion of for series, so this is by the Cauchy criterion, there exists a number n such that the sum from n plus 1 I equal to n plus 1 to infinity mbi is less than or equal to epsilon. This is just from the convergence of this series infinite sum mbi. On the other hand, we can let f be the union from 1 to n of these bi's, and then I claim that the measure of E symmetric difference f is less than or equal to epsilon or 2 epsilon. Let us see what it is. I think it is 2 epsilon. So, how do we compute this? So measure of E, so this is the proof of the claim. This is less than or equal to the measure of E minus F plus the measure of F minus E, and note that E was covered by this by these boxes Bi, and so when you leave out finitely many boxes, so F was this finite union from 1 to n, then this is a subset of the union I equal to n plus 1 to infinity of Bi. So therefore we can write this as the measure of union I equal to 1 n plus 1 to infinity Bi plus the measure of F minus E, which is I equal to 1 to n Bi minus measure of E, because both these are finite, so we can simply, and measurable, so we can simply write it as a difference. So now this is less than or equal to the sum n plus 1 to infinity of Mbi, and the next term is simply less than or equal to I equal to 1 to n Mbi minus Me, and this is again less than or equal to I equal to n plus 1. So the first term remains the same, but I let the second term go to infinity in the sum minus Me. Now note that this part is less than or equal to epsilon, and this part is less than or equal to epsilon by the choice of our Bi. So this is less than or equal to 2 epsilon. Now if we let C to be the sum I equal to 1 to n chi of Bi, then chi E and C differ on a set of measure at most 2 epsilon, since this set where they differ is precisely E delta F, and which has measure less than or equal to 2 epsilon. So this means that the L1 norm of chi E minus C, which is by definition, this is now a simple function, this is equal to this measure of the symmetric difference of E and F, and this is less than or equal to 2 epsilon. So here this is our F and this is our C, and we have proved this result of approximation by step functions when F is a single indicator function of a measurable set with finite measure. Now we consider a more general L1 simple function of the form 1 to m, say alpha I chi of Ei. So this is an L1 function, and now choose for each I in 1 to up to m a step function Ci such that the norm of chi Ei minus Ci, the L1 norm, is less than or equal to epsilon over 1 plus summation I equal to 1 to m of alpha I. So here note that alpha i's are all positive real numbers and Ei's are disjoint measurable sets, because F is a simple function. So if we choose our Ci for each I such that this L1 norm is less than or equal to epsilon by 1 plus the sum of all these alpha i's. Then we have that for C equals the sum alpha I Ci, I equal to 1 to m, the norm of f minus C is equal to the sum alpha I equal to 1 to m chi ei minus Ci. So this is by construction, and now we can use triangle inequality. So using triangle inequality, then the norm of f minus C is less than or equal to the sum I equal to 1 to m alpha I, and then you have the norm of chi ei minus Ci, the L1 norm, and now these are less than or equal to epsilon by 1 plus summation alpha I equal to 1 to m. So this is less than or equal to I equal to 1 to m alpha I epsilon over 1 plus summation I equal to 1 to m alpha I. And now note that this is nothing but summation I equal to 1 to m alpha I over 1 plus something, so 1 plus the same thing, and then epsilon, and this is less than or equal to epsilon because this whole thing is less than or equal to 1. So from unsigned simple function with a single which is a single indicator function of a measurable set, we find a step function which is close to it, and then we can deduce the general case simply by using triangle inequality, and then similarly we can extend this to first real valued and then complex valued L1 functions. So this shows part 2.